Hello, class. Hope you're doing well. If I don't seem as upbeat as I usually am in these videos, and I do, I mean, for those of you that know me, I am a pretty upbeat person, but I try to be a little more happier than normal in these videos. I'm sick. I've got some sort of stomach issue, and I'm feeling pretty under the weather. So sorry if I'm not my usual upbeat self. Kind of dragging a little bit here. I got out of bed at 11 a.m. today, and I went to bed before 10. So yeah. Anyways, I wanted to tell you about decaffeinated coffee today. So this is something I go through and I kind of harvest these articles. Say, oh, it looks kind of interesting, and I know I was talking a lot about the Nobel prizes that are recent. I even saw one that was looked interesting on about proteins, and I was like, you guys have got enough of that. So let's talk about something more society focused, like decaffeinated coffee. And interestingly enough, I tend to be, me personally, I'm pretty sensitive to caffeine, and if I do drink coffee, which is very rare, it would be with the Swiss water method, and that's covered in here, and that's the best as far as taking out the caffeine. But the cheap way of doing it is using methylene chloride. So caffeine is a molecule. It tends to be more soluble. It has different solubilities, and caffeine can also be soluble into certain solvents, and methylene chloride is one of them. So using this, then the what do you call it, the soaking the coffee beans in the methylene chloride can strip out the caffeine. And then part of it, though, is some of the methylene chloride is stuck in there. And in methylene chloride, it's dichloromethane. It's one carbon with two chlorines and two hydrogens. It's also polar, so it makes it a good solvent. And it's a known carcinogen, and I can tell you this stuff smells terrible. I do not like the way this stuff smells. So me myself, I'm a physical chemist. I tend not to work with chemicals as much, but I do know what the smell of methylene chloride is. A lot of chemistry is stinky. So, but with that, they so soaking the beans in that will will strip out the caffeine, and then when they go and roast the beans, there's still a little bit of methylene chloride stuck in the beans, and the nice thing is when you roast it, it gets rid of most of it. And I also think it's kind of interesting with this article that so the FDA is the one that controls food and drug, and looking at the different the different parts of the government, and the U.S. government it's very compartmentalized. For instance, for me myself, I have grants from the National Science Foundation, and they're very strict. I cannot interact with anyone. Well, I can, with my job, but with the grants, anyone that's pre-med or pre-farm or pre-vet can't get money from me using the grants, because that's under the jurisdiction of the National Institute of Health. So it's funny how the government, they're very clear on, this is your lane, stay in your lane. So where the Environmental Protection Agency says get rid of all the methylene chloride, but the FDA is like, meh, it's okay. And it does turn out that most of the methylene chloride is released in the processes. There's not that much. I guess for me it doesn't affect me that much because I generally don't drink coffee. But there are other ways to get rid of caffeine. The more common way is one of them is called the Swiss water method, and this article covers it. You basically go through various stages of hot water, and here it is, Swiss water process, and uses only water, and of course water is safe. And I'm not as much of a connoisseur to know that how much it it affects the flavor. So I'm the wrong person asking that. But also using supercritical CO2. So what is supercritical? So a gas, generally speaking, three states of matter: solid, liquid, gas. Solids have set forms and set volumes. Liquids have set volumes, but they don't have set forms. And gases neither have set volumes or set forms. But if you take a gas and you compress it hard enough, so the atoms and or molecules of the gas, I mean, whatever gas it is, the atoms and our molecules are pushed further into each other. They're much closer, and then that fluid then starts to act more and more like a liquid, but it's not really a liquid. So liquids, for instance, there actually is an attraction between the atoms and our molecules that keeps it in the liquid phase. But the supercritical, it just has to do with the extreme amount of pressure that it's added there. And then certain things happen under supercritical states. Carbon dioxide, for instance, is a nonpolar molecule, and generally speaking, nonpolar can only mix with other nonpolar. Same thing with polar, tend to mix with polar. So, and caffeine is a polar molecule. So, but under the supercritical state, the carbon dioxide can start to strip out polar molecules. So similar things happen for water. Water is a polar molecule. Supercritical water actually can pull out nonpolar stuff. So that works both ways. And it has to do also with the temperature. The temperature is just so high that the attractions of the electron clouds and the dipoles, the temperature is so high that effect just kind of goes away. So that's the reason why it is for water and also supercritical fluids. So it's kind of a unique state of matter there. And that's how carbon dioxide can do that. And what's nice about carbon dioxide is it's cheap and it's safe, right? So, and also, if you want to do the carbon dioxide method, then you take the supercritical fluid. So after the solid beans go through, and then the supercritical carbon dioxide, you just lower the temperature. The carbon dioxide goes away and it leaves pure caffeine. So that's another way you can well, I guess it wouldn't be pure, but it would be a very concentrated form of solid caffeine. Caffeine's a solid. It's a crystal. It's a white crystal. So it's interesting. You gotta be careful with pure caffeine though. It's kind of dangerous because it's a stimulant, right? So if you have a couple grams of caffeine, because like in a cup of coffee, it's like 100 milligrams of caffeine. So milligrams, zero point 0.1 grams. And so if you're handling, say, like 10 grams of coffee, that's equivalent to 100 cups of coffee, right? So that's a lot of caffeine, and that can have some psychotropic effects on and I mean just in as a stimulant, right? It can have effects on humans. So I don't recommend you do that. So. But in some places they do sell pure caffeine. And I like this statement at the bottom here. It's not like chemical engineers and chemists can't figure out how to make better decaffeinated coffee. It's a question of, are people willing to purchase the coffee at a price point that makes it economically viable? I mean, we have the technology, we can do it, but I mean, this goes back to economics. So this is a household product, and I mean, there are very effective ways, and the Swiss water method, for instance, it gets rid of the vast majority of the caffeine, better than the supercritical CO2, better than the methylene chloride. But I mean, the question is the consumer willing to pay the premium for that? So it really depends on the person. So it's interesting to see that, and so this is something with that we have every day of our lives. So coffee, I don't drink coffee, but I like this article because it talks about something that a lot of people do drink coffee, and I think it's like 80% of the population is chemically dependent on caffeine in one way or another. So a lot of people are addicted to caffeine in one way or another. So I guess I'm one of the lucky 1 in 5 people that's not. Or I don't know. Maybe I'm unlucky because I'm missing out on all the delicious coffee and tea that people drink. But it's interesting. It also deals with solubility rules, and so, we do talk about solubility rules, and so here is a practical application. And what we don't talk about in this class very frequently is economics. So I like how this article brings in economics. I mean, there are lots of things that we can do, but I mean, the economics is concerned. There's a cost for everything. So, well, I hope you enjoy the article. I hope you are doing well. The disease that I have, it's gastrointestinal. So I am pretty contagious, and I've been for instance, I didn't go to there's a Wednesday lunches at Windward, and I did not go. I thought about going, but I just like I can't justify going there, and because that's how you spread gastroenteritis is through food. And I was like, if I'm touching the same surfaces that students are touching, that I'm probably going to infect a bunch of people. So I'm going to stay away until I get over this. But it's not airborne. So I did. So what's nice about this? It's not airborne, so I don't have to worry about that. But by touch, you can spread this disease. There's other diseases. Ebola, for instance, can be spread by touch. But I don't have Ebola, so although it's just given that as an example. But okay. I hope that you're doing well. I hope you are not sick. It's never fun to get sick, and I hope. And if you have any issues or anything like academic issues, mental health issues, or basic needs, let me know. I'll do what I can to help. So I hope the rest of your week goes well, and aloha.